This video is for 6.6 interest formulas. There's 8 questions on this one. An amount of $41,000 is borrowed for 6 years at 5.75 interest, compounded annually. Okay, compounded just means we're using compound interest. And let's just remind ourselves of what that formula is. The total amount will be P times 1 plus R divided by N raised to the NT power. Now let me explain what each of those parts are. Okay, that right there is the principal. Okay, the principal, I think I spelled it wrong, but whatever. The initial amount, where we start, our starting amount. Okay, and this right here is the rate, and it's usually compounded annually. It could be compounded quarterly, so annually, quarterly, monthly, and some questions even have it daily. Oh, I guess there's also weekly. Okay, now each one of these, that means it's once per year. This is per year. So once per year, 4 times per year. Monthly is 12 times per year. Weekly is 52 times per year. And daily is usually 364 times per year. So let's go through this. Now the N is the number of times it's compounded every year. So that would be this number right here. If it's annual interest, and it almost always is APR, or annual percent. So so that's the number of times per year. Okay, and that's the same number right there and right here. Same number. And then T is the number of years. Okay, so that's my equation. So let's plug this in. We've got 41,000. So 41,000. 1 plus, what's my rate? It's 5.75, and that has to be a decimal. Okay, decimal. So to turn that into a decimal, we move the decimal 2 times, giving us 0.0575, 0.0575 over how many times per year? It's compounded annually, so that means we put a 1 raised to the same number here, 1, so that number just goes right there, and the term per year. If the loan is paid off at the end of that period, how much must be paid back? It's 6 years. Okay, so times 6. Now, please don't do this in your head. Use a calculator. And it doesn't have to be a fancy calculator. It can be just a very simple computer calculator. Let's see. Put it right there. So let's solve the parentheses first. Okay, what's 0.05? Oh, I don't even need a calculator for this. What's 0.0575 divided by 1? Okay, that's 0.0575. So I've got 1 plus 1.0575. Now what's 1 plus that? Well, it's just 1.0575. Okay? What's 1 times 6? That's 6, so that to the 6th power. So let's go ahead and use the calculator to figure that out. Just a simple calculator. 1.0575 raised to the 6th power. Enter. Okay, and we're going to get a big number here, and that's fine. Interest is always messy. So we've got 41,000 times, and I'm going to go 1.3986. I'm just going to go a few decimal places. So, or you can just hit like what I'm about to do here, times 41,000, enter. And so when we pay it all off, we're going to be paying 57,341.11 cents. And that's the answer. Number 2. A certain forest covers an area of 3,600 kilometers squared. Suppose that each year this area decreases by 4.75%. What would the area be after 12 years? So this is a decaying problem, okay? And all we're going to use is the exponential function. When I see here we have a calculator. I probably did on number 1 too. So we take the initial amount, 3,600, and then times the rate. Well, what's the rate? It's decreasing by 4.75. So we take 100% minus 4.75, and we get, and I'm just going to use the calculator. We get 100 minus 4.75, and we get 95.25. That's what goes in here. Okay? If it were increasing, we'd add, and that's what would be going in there. But we're decreasing, so we subtract. Now that has to be a decimal. That's 95%. So we've just got to move the decimal 2 places over. And so we times 0.9525. And we want 12 years. So we're going to put a 12 right there. Now let's type this into the calculator. 3,600 parentheses 0.9525 raised to the 12th power, and we see the answer will be 2007. Round your answer to the nearest square kilometer right there. So instead of 7, I'm going to say that's 2008. Because the 6 means I'm closer to the 8. Number 3. A deli sandwich is placed inside a cooler. As the sandwich cools its temperature in degrees Celsius after 10 minutes, we can follow this formula right here. And we see it's an exponential geometric equation or formula. Find the initial temperature. This number right here, the very first number before the parentheses, that's always my initial temperature or my initial value or whatever. That's my starting point. So the initial temperature is 21 degrees. Okay. Now, is it growth or decay? we can always tell that by this number right here. If it's greater than 1, then that means it's growing. It's growth. If it's less than 1, that means it's decay. So it's always that number right here. So I see in this example, we are decaying. We're getting smaller because it's smaller than 1. And by what percent? To find that, you always take 1 minus, and you can do the 1.00, minus that number, 0.96. Okay, and that would be 0.04. So that tells me, now we move the decimal 2 times, it's 4%. So it's changing by 4%. So if it's ever decay, and let me switch to a clean screen here. If it's ever decay, you take 1 minus whatever is inside the parentheses. Okay? Whatever's inside those parentheses, it'd be 0 point whatever. That is your percent of decay. Now, if it's growing, then you just ignore. So here's that number here. It would be a 1 point blah, 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 whatever. If it's growing, then you just simply ignore that. Okay? And you got 12%. So that's your percent growth. So what's actually happening is in decay, you take 1.00 minus the decay, and that gives you your percent of change. With growth, you do it the other way around. You take your growth minus 1.00, and that will give you your percent of change. Okay, so you got to know what's going on. The way I remembered, if it's 0, I got to take 1 minus that number. If it's greater than 1, I take that number minus 1. So you always want the bigger number on top, whether it's the 1.00 or the number in the parentheses. And that's how I remember how to do it. So in this case, we took the 1.00 on top because it was the larger number. Number 4. Study has shown that the population goes on, and it's this formula right here. Okay. Find the initial population size. Okay. Any type of growth or decay, right there, that first number is my initial. So that tells me the initial population size is 340. Now, with the next one, is it growth or decay? We look at this number. If it's greater than 1, it's growth. If it's less than 1, it's decay. In this case, it is greater than 1, so that tells me it's getting bigger, it's growing. Okay, by what percent? If you remember, in growth, you take that number on top, but my little shortcut, you always want the bigger number on top. So is 1.00 or 1.33 bigger? Well, in this case, 1.33 is bigger. So minus 1.00, and you have 3, and now we just move the decimal 2 times, giving us 33%. Just like that. To begin a bacteria study, a Petri dish had 1,600 bacteria cells. Each hour since, the number of cells increases by 8.4%. Let T be the number of hours since the start of the study, and let Y be the number of bacteria cells. Write an exponential function with the relationship. Okay, so we have Y equals the start times the common ratio, okay, to the T power, because growth, that's what we're going to look like. Now, what's our starting amount? Our starting amount is 1,600. Okay, and then what's happening? What's our ratio? It is increasing by 8.04. So that means with a growth formula like this, we take 1.00 and plus, because we're increasing by 8.4%. Okay, so that's 8.4%. Let's turn that into a decimal. Make that a little easier to follow. 8.4%, if I move that decimal 2 times, that's 0.084, so 0.084. Therefore, we can line it up just like that, and we get 480.1, and that goes in here, 1.084. So anytime it's growth, you just add it. If it's decay, you subtract it. If it's getting smaller, you just subtract it. Still always the 1.0 on top, and then raised to the T power, because we don't know how much time. So that is our equation. We have 1600 times 1.084 raised to the T. Just like that. Number 6, there was a sample of 450 milligrams of radioactive substance to start a study. Since then, the sample has decayed, so in this case it's going down, by 8.4% each year. Okay, so it wants us to now write an exponential function. Exponential function is y equals the start times the ratio or the amount of change raised to the T power. So let's plug in what we know. What's our starting amount is 450 parentheses. And what's our rate? It's decaying by 8.4%. So that means I take 1.00 minus, and let's move the decimal 2 times, 0.084. Okay, and just for accuracy's sake, I'm going to use just a simple calculator. And I'm going to take 1.00, but just 1, minus 0.084. 0.916 is my answer. So 0.916, and that's also what goes here. 0.916 raised to the T power. And there we are. That's my answer. So 450 parentheses 0.916 parentheses raised to the T power. Oh, I wonder if I did this. Don't forget the y equals. I almost forgot that. I wonder if I forgot that in the last one. Yes, I did. Don't forget the y equals. There we go. Okay, Because remember, it says it wants us to relate y to t. So that would be y equals that. All right, number 7. A can of soda is placed inside a cooler. As the soda cools, its temperature C of T in degrees Celsius, T after T minutes has been given by the function. All we need to really focus on is this function right here. Good. What's the initial value or the initial starting point or the initial temperature? That would be that right there. The first number is my initial temperature. So it's 27 degrees. Is it growing or decaying? Well, right here, we see it's less than 1. If it's less than 1, it's decaying. By what percent is it decaying? Remember, we take 1.0 minus a number or that number. In this case, that number is smaller than 1.0, so we always want the bigger number on top. And we minus them, okay? And we get 0.12. Okay, if you'd use a calculator, that's fine, but it's 0.12. And to show you, we just borrow. 10 minus 8 is 2, 9 minus 8 is 1. So it is going down by 12%. Move that decimal over 2 times, and you get 12%. Another one, very similar. Here's the equation. What's the initial value? It's right here. So 532,000. Is it growth or decay? Well, this number is bigger than 1, so it's growth. By how much? To figure that out, we take the larger of that number, or 1.0. In this case, this is bigger than 1.0, so I'm going to take 1.09 minus 1.00 equals, and it's 0.09. So move the decimal 2 times, and we get 9%. So that just turns into a 9% right there. So that's how you do it. There's a few things to remember there. Hopefully this helps you get through it. If you have any questions, let me know.